Hello, I am Professor Gadgil. I am going to discuss structural dynamics with particular emphasis on seismic analysis of buildings. My entire presentation today is uh, going to cover following topics. That is, firstly, I will be giving some introduction about the problem that we are going to discuss. Then we will be talking about classification of structures. Then the loads coming on the structures, then the deterministic and non-deterministic analysis or the stochastic analysis or the forces that we have. We will be discussing about the dynamic forces, the types of dynamic forces to be considered in structural analysis. Then we will be discussing static and dynamic analysis, the basic difference between the two. The problem with seismic analysis will be discussed subsequently. Thereafter, a single degree of freedom system will be discussed in detail for its free vibration analysis. Then the force vibration of single degree of freedom system will be considered, which will be a important step towards carrying out the seismic analysis of the structures. Then the single degree of freedom system subjected to ground motion will be discussed, which will be later on extended to modal equations of motion for ground motion, that is for multi-degree of freedom system. A simple example will be considered for response of multi-degree of freedom system subjected to ground motion, wherein the analysis will be performed on the response history response history calculations. The response spectrum analysis will be introduced subsequently, and then seismic analysis using response spectrum method will be discussed as a concept, and there will be a problem solved completely using the response spectrum method as well as the response history analysis. So this is the overall guideline that is to be followed in the present lecture. In the introduction, now I am going to define what is the primary objective of structural engineering activity. The primary objective of structural engineers' work is to plan, design, and detail a structural system which will carry safely the loads coming on it. Which means, now if you look at the definition, it means we have firstly a structural system. Secondly, it has to carry loads. Thirdly, the loads have to be carried and resisted safely, so that the structural design meets the requirements of the end users. Now, the first step that we are considered in the major activities of a structural engineer is he has a structure, which means, now let us see what we understand by a structure. So we say that structure is an assemblage of members suitably connected to each other and supported so that it carries the loads coming on it safely and carries the load to the foundation. Which means the basic building block of a structure, whatever that we have before us, is a member or an element which may be one dimensional, two dimensional, or three dimensional. Now, when we consider the structure, then we say that as a common man, this structure develops different images or understanding in his mind. So, for a layman, a structure would be a buildings, tall buildings or medium-rise buildings, or bridges which are used for covering distance over either roads or rivers and so on. Then we have fluid containing or fluid containment tanks or the water tanks. Then we have the retaining walls which are used to retain earth. Then we have the dams, massive structures which retain water on one side. Then we have the aircraft which carries tremendous amount of load and it moves from one place to the other place in air. So we have to carefully, or the common man understands aircraft as a huge flying structure. Then there are ships which are also understood by a common man as a structure which floats on water. Then we have the automobiles mounted on wheels which carry loads either in the form of cargo like the truck carriers or oil tankers being transported on trucks and so on and so on. Then we have the tunnels going through the mountains for covering the distance between two places in the shortest possible manner. So we have the tunnel with its lining, which is to be properly designed to carry the loads coming from above, the soil above, and so on. Then we have the jetty, which are designed or which are meant to berth the ships at the shore. Then we have the cranes, the tower cranes, which are used in modern day buildings, or the huge cranes in warehouses and so on. And we have balloons or the air inflated structures, which are also in great use over the years. The classification of structure that we have seen is the way a common man understands it, while for an engineer, the structure carries different, you can say, definitions or understanding. An engineer may call a structure as a beam, which is primarily a member which is subjected to transverse loads and carries bending moment and shear forces. Or you have got a columns which is primarily meant to carry axial force and the bending moments. Then we have the arches, which are there to span large distances with aesthetic sense in it, carries primarily axial force and some amount of bending moment or shear force. Then we have the cable structures, which are primarily meant to take only tensile forces. Then we have the trusses, which may be either plain truss or the space truss, where the members are expected to take only primarily axial force. Then we have the frames, which are either the plain frame or the space frame, which are where the members are subjected to axial force, shear force, bending moments, torsional moments, and so on. Then we have the floor with grid system, which carries primarily the load in the direction perpendicular to the plane in which the structure lies. The floor grid system members carry the bending moment, the twisting moment, and the shear force. Then we have the slab, which is a two-dimensional structure which carries moments in its transverse plane and the shear force through the thickness. Then we have the shell, which carries all types of forces. Primarily it is meant to carry membrane forces, but in addition to that, local bending stresses or local shear forces are also developed. Then we have the folded plates, which are meant to carry again, like shell, the membrane forces, but in addition to that, some local bending moments are also present. Then we have the three-dimensional solids, like the foundation blocks for machine supporting machines or massive foundations below the chimneys and so on and so forth. Then we have plane stress problem, we have the plane strain problem, the axisymmetric problems, and so on and so forth. So we see that for an engineer, the understanding of structure is different, while for a common man, it is quite different. Now, as far as the primary objective of structural engineer's activity is concerned, is that we have a structural system, it has to carry loads and the load is to be carried safely. So once we say that it has to carry loads, now let us see what kind of loads are expected on the structure. So we say that the loads applied on the structure generally comprise of the following list, though there might be few more loads also to be considered. So we have the self-weight of the structure, which depends on the material that is being used. We have the imposed loads like the floor finish or the live load and so on. Then we have the wind load externally applied on the buildings. We have the seismic load generated due to the disturbance at the ground level. We have the temperature loads. Over the years, we see that the maximum and minimum temperature at any place varies by a wide margin. To that extent, the structure expands and contracts. So sometimes we have to consider the effect of this expansion and contraction in the design of structure. Then we have the shrinkage and creep concrete, which also develops, you can say, the additional internal forces which have to be considered in structures over a long period of time. Then we have the fatigue, which is developed when rotating machines are to be supported by the structure, and due to the continuous uh, development of alternating internal forces, the phenomenon of fatigue gets set in, leading to sometimes failure of the structure. Then we have the lack of fit. So in the fabrication, there is always some tolerance expected in the fabrication of the members. So if the members are too long or too short by a small margin, then we try to force fit it, resulting into additional forces in it. Then we have the pre-stress to be considered in the analysis when we are considering long span bridges or large span slabs and so on, where these days the pre-stressing forces are being considered for efficient design of those structures. Then we have the buoyancy forces, which are to be considered for floating structures like ship. Then we have the pressure, either the internal pressure in case of pipelines or gas tanks and so on, or the external pressure when we have got the pipelines going at the seabed level, where tremendous amount of external water pressure is to be considered. And we have the electromagnetic forces to be considered for structures like a transformer frame and so on, where huge amount of current and the associated electromagnetic forces are developed. Now that is the general description of the loads. Now loads are further classified sometimes in two categories: the deterministic load and the non-deterministic or stochastic forces. Deterministic forces are those which are fully known for their magnitude and direction, their point of application, the time duration and the time variation also are the conventional deterministic forces. So if everything about the force is known precisely, then we say that it's a deterministic force, and the analysis is then the deterministic analysis. Sometimes the force data is not precisely known. It is known in terms of some statistical properties. Forces which are not fully known for their magnitude, direction, or the point of application, the time duration and time variation, but are known in a probabilistic manner or in terms of statistical properties like an average or a mean or standard deviation and so on. If you have to deal with such forces, then we call such forces as non-deterministic, and the analysis is then the non-deterministic analysis or stochastic analysis. We further say that the forces that we are considering, for most of the categories that we have considered, they are all static forces. But there are some forces or some situations where the forces are to be treated separately. A force which varies with time, then we call it as a different type of force because it induces different phenomenon in the structure itself. The force has got four characteristics. One, its magnitude. So you might have a force whose magnitude changes with time. The force has got a direction. So we can say force that we are considering might be a force whose direction changes with time. We have to consider for force for its point of application. Now, if point of application of the force also changes with time, like moving loads on the bridges and so on, then we say that, oh, that also is a different type of force. And we have sometimes a situation where the support of any structure itself undergoes vibration or movement. So that is, say, under seismic condition, we have to consider or treat that type of force separately. So we say that these are the different types of variations that we have to consider. Some of the force variations are now indicated. One is the harmonic force, which is developed due to many times the rotating machinery which is supported on structures. The rotating machine can develop force which changes with time for its direction, but if you consider its component only in one direction, then it can vary from a plus value to a minus value. Then we consider another type of variation, which is when the magnitude of the force varies with time, like an explosion. So in explosion, there is a sudden buildup of force, and then there is sudden drop in the magnitude of the force. So within a very short time, the entire process takes place, and the force varies with time in that fashion. Then we have another type of force which varies with time, which is the impact type of force. So if a heavy object or a missile is thrown on a structure, then we say that it gives rise to a very large force within a very short time, and later on, as the effect of that massive velocity of the falling object is reduced, then later on it's only the weight of the missile which the structure has to resist. So we have a force which varies with time, but the entire variation is in a very short interval of time. Then we have a force which changes its position on the given structure. So we have the moving loads over here. Now the moving load on bridges, continuously the vehicle keeps on changing. So by the time the force structure tries to develop enough reactions or internal forces, the position of the structure, the load changes. The result of that is continuously the structure is subjected to displacements which are changing with time, giving rise to bending moment changing with time, and so on and so forth. Then we have another type of force that we have considered, which is the ground motion that we are considering. So if you have got a massive building resting on ground, and if that ground itself shakes during earthquake, then we say that, oh, that may give rise to enormous amount of vibrations in the structure, and we will have to consider the effect of such vibrations in the analysis and design of the structure. Then we have considered so far the static type of forces or the dynamic type of forces, the deterministic as well as non-deterministic. Now, once we say that the forces can be static or can be dynamic, then we say that if the forces are either static or dynamic, then the analysis will also be accordingly a static analysis or a dynamic analysis. In static analysis, as we see, the forces are constant. The result of that is the response is also constant, your bending moment is constant, the shear force is constant, the deflection is constant, and so on and so forth. The examples of such types of forces are the self-weight, the gradually applied live load, or the normal wind load, which will give rise to a constant force on the building, and so on and so on. Or if at all it varies very gradually, so we don't have to consider its variation. In dynamic analysis, when we are considering the structure being analyzed due to when it is subjected to dynamic loads, then we say that we have to deal with a situation where the force varies for its magnitude, direction, or point of application, or the support motion. So all these things can be present. The result of that is the response of the structure also varies with time, and the result of that is we have to consider that type of analysis separately. The examples of such types of forces which we have considered earlier is the high speed rotating machines, or the compressors, like the compressors or the generators or the pumps. Then we have the explosions occurring in the vicinity of the structure, or the impact, or in case of forging hammers also large amount of impact forces are developed at the foundation level, and so on. Then we have the moving loads on the bridges where the force changes its point of application continuously, and we have the ground motion during earthquake, and so on and so forth. So we now see that we have the static and the dynamic analysis giving rise to different types of concepts over here. Now we say that the static response that we are considering when the force is considered as constant depends on the type of force that you have got. It may be UDL, or it may be point load, or it may be any other variation that you are considering. It will, the response of the structure, therefore we say, depends on the stiffness of the structure. If the structure is very stiff, it will give some response in terms of displacements and so on. The static response that we consider in terms of deflections is very simple for static analysis, and that is we have got force upon stiffness giving rise to static response of deflection. In dynamic analysis, we say that the dynamic response itself is a function of type of force, that is how it varies. whether it's an impact type of force or an explosion type of force, or it is harmonic force due to rotating machines. So depending on the type of force and its variation with respect to time, the response will change. The same force varying in explosion will cause some response, but if the force is not explosion due to explosion, but is due to impact, then it will give rise to another response, and so on. It further depends upon the response of the structure, of course, is dependent on the stiffness of the structure. The same force will be you can say resisted differently by structures with very large stiffness or those with very small stiffness. And further, the response depends upon the mass of the structure, because due to these forces which vary with time, the structure is subjected to vibration, and vibration gives rise to change in displacement of structure from time to time, giving rise to velocity at different points. And velocity is also not constant, so it gives rise to acceleration, which generates internal forces in the structure like the inertia force. That inertia force is the additional force which the structure is expected to resist. The dynamic response, therefore, due to any force, which is the dynamic force, of course, will depend upon, firstly, if the same force is applied statically, okay, there is some response generated by the structure, but if the force is applied dynamically, then the response gets magnified or modified. So we say that we have the dynamic response given by static response if the force is applied statically, and there is a factor which we have to consider called as the dynamic magnification factor. Now this dynamic magnification factor is the most important concept in dynamic analysis, because it indicates as to by what margin the response gets modified when you are considering the dynamic nature of the force itself. The dynamic magnification factor that we have to consider, it depends upon the type of force. The same force applied in explosion or applied in impact or applied as a harmonic force will cause different dynamic magnification factor. Further, it depends upon the duration of the dynamic force. If duration is too short, there is some magnification factor. If it is too long, there is another magnification factor. It further depends upon the period of natural vibration of the structure, denoted as T, which is a function of the properties of the structure like its stiffness and mass. And of course, the dynamic magnification factor also depends on damping in structure, which is the energy loss mechanism present in and around the structure. But we will not go into the details of that, because many times its effect is only small compared to an undamped structure that we otherwise consider. So that is all as far as the dynamic magnification factor is. Now we consider the force of importance for today's discussion, that is the seismic loads. The seismic loads are a very peculiar case of dynamic force. In case of all the loads that we have been discussing so far, like an explosion or an impact type of force or force generated by the rotating machines, we say that there is a definite information about the force that we have to consider. In case of earthquake, there is a lot of uncertainty. I don't know what magnitude of earthquake is going to hit the structure, in which direction the waves will be coming, and how long the earthquake will last. So that is all unknown. You have to only speculate or see the past history and then see as to how I have to take all those factors and then try to imagine or try to estimate what kind of force is to be considered. No precise information is available. The occurrence of earthquake itself is uncertain. Sometimes during the lifetime of a structure, no earthquake might hit the structure, but nevertheless, we have to keep a provision that if earthquake really hits the building or the structure, then it must withstand. So we have to consider the probabilistic method of design in this situation as to what is the probability of structure being hit by a very severe earthquake. So we'll have to consider that, and then the structure is to be designed accordingly. So we say that entirely a new concept is required to be studied, in considering the earthquake analysis. And we have to further indicate that we just cannot design a building which will be able to resist any type of earthquake. Impossible. We will say that as far as the structure is concerned, we just cannot design a structure to withstand any type of force. We have to consider, say that the structure will generally resist certain intensity of earthquake in a safe manner. Some more severe earthquake can cause some damage to it, not leading to collapse, while other very severe earthquake might damage the structure to such a great extent that we may have to pull it down later on and then build a new structure. So our idea is always to see that the minimum damage is caused to the structure during normal or moderately severe earthquake and so on and so forth. So we say that the seismic analysis has got to be performed in a very, you can say, methodic manner, but the problems are quite different, and we have to consider some probability of occurrence of earthquake, probability of saving the structure from complete destruction, and so on and so forth. Having considered that, now let us consider the free vibration analysis of single degree of freedom system. So we have this simple spring mass system. The spring has got a stiffness K, there is a mass M attached to it, and if this particular system is set into vibratory motion, for example, now we consider simple vibration of this spring mass system. So we will just consider the natural frequency of the spring mass system and see as a simple visual example as to how we can consider the real vibration of a spring mass system. So we will be considering few springs over here. They have got different stiffnesses, and there are some masses here from very heavy to very light mass and so on and so forth. So we have got three springs with three different masses, and if we consider the spring of stiffness K and mass M, we will see in a minute that the frequency of vibration for this is given by square root of K by M. So if I consider varying mass, that means same type of spring, but different masses are attached to it. So here very large mass is attached, so it vibrates very slowly because we have got the frequency given by root K upon M. So if the M mass is in the denominator, it vibrates at a very low frequency. While different springs are considered for same mass, then we will say that the spring which is very stiff will vibrate very fast, while that which is very weak will vibrate very slowly. Now having considered that, now let us consider the simple problem of spring mass system for its governing equation. So we have the mass M set into vibratory motion. The mass at any instant has got a displacement from its static position by y. It has got a velocity dy by dt in the downward direction, and in the downward direction it has got an acceleration d2y by dt square, giving rise to, for this particular mass, the inertia force, mass times the acceleration, the extension of the spring as equal to the stiffness of the spring multiplied by its elongation y. So we say that we have the inertia force m into d2y by dt square plus the elastic force ky, keeping the mass in equilibrium. So we say that that is my governing equation of motion or equation of equilibrium in dynamic state. This is a second order ordinary differential equation with constant coefficients of k and m. The solution of this, we will not go into the details of that, consists of a cos omega t plus b sin omega t. There omega is the natural frequency of vibration, that is omega square equal to k by m radians per second, is the so-called natural frequency of vibration. So we say that we have got this equation m d2y by dt square plus ky equal to 0 giving rise to a spring mass system, or from a spring mass system we have the spring mass system with a frequency omega square equal to k by n. So we are deriving this equation for a spring mass system. In reality, if we have got, for example, a cantilever beam, then we say that even cantilever beam is a spring whose stiffness is the force to cause unit deflection, which in this case is 3 by L cube. So I have the cantilever of span L, mass m, ei, the flexural rigidity constant. So it has got a bending stiffness of 3 ei by L cube, which is the stiffness to cause unit deflection in the free end. Similarly, if you have got this simply supported beam with point mass at the center, then we say its stiffness is 48 ei by L cube, that is the force required to cause unit deflection, which means it has also got a spring characteristic of that stiffness. If you consider a plane frame with very rigid beam, then we say that we have got columns of flexural rigidity ei, there is mass m at the top, the height of the column is L. So we say that the stiffness of this particular frame for lateral vibration is now 24 ei by L cube, 12 ei by L cube for each of the column, and we have two columns. So we say that any structure that we consider has got some stiffness, some mass. Accordingly, it will be a vibrating system later on when subjected to some disturbance, and it has got some frequency of vibration which is a function of the stiffness and the mass over there. Now we consider the same spring mass system which is subjected to some dynamic force. So we have got some dynamic force over here. Then we say that now we have got three forces. One, the inertia force. Two, the elastic force in the spring, that is K into Y. And there is this external force F0 into Ft. So this is some reference magnitude, and this is the time variation of that force. So we say that the general solution for this, again without going into the details of its derivation, we say it is a cos omega t plus b sin omega t, that is if there is no force at all, and due to the presence of the force we have got 1 upon m omega into integral of Ft, that is the variation, that the force that we are considering, into sin omega t minus tau. Tau is at any instant where tau goes from 0 to any. So we have got now this particular spring mass system subjected to some dynamic load. So if we know the variation of that force with respect to time, then we say that substituting that variation, we will be able to get the response of the structure subjected to that dynamic load. So now we say that if we have got a harmonic force, for example, then the same equation, when I substitute the equation for harmonic force, then I get the solution of the equation as a cos omega t plus b sin omega t, that is for free vibration part, into F0, that is the force that I am considering, upon K, the stiffness. Inside bracket I have got 1 minus p square upon omega square into sin pt, where p is the frequency of that harmonic force. So I might have a force which is applied at 100 rpm or 1000 rpm. So accordingly I will have this force with a frequency p, so many radians per second or cycles per second, giving rise to a response given by this equation. If I consider the rectangular pulse applied on the given structure, that is a force which is applied over a period of small duration, say t, but that force remains constant for that time, and later on the force is 0, then F0 is the force which is now applied as a rectangular pulse. Then the response is given by F0 upon K into 1 minus cos omega t, that is force vibration part. The free vibration part of course remains the same. If you have got the triangular pulse applied, then it is the force vibration part is F0 upon K into 1 minus cos omega t plus F0 upon K into Td, where Td is the duration of the force, into sin omega t upon multiplied by omega minus t. So we say that we have got this as the effect of different variations of the force, and if we summarize them, then we get the graph called as the displacement response spectrum, which means for a spring mass system whose period of vibration is t, if you apply on it rectangular pulse load or a half sine wave 4 type force or a triangular force, then the force time diagram is now indicated over here. On y-axis we have the maximum response ratio, that is Rmax over here, that is your maximum dynamic response to static response ratio. So for rectangular pulse that ratio is 2, while on the x-axis if you consider it is the ratio of T1 upon T, that means in how much time you will be getting that maximum response. So for rectangular pulse, roughly in that ratio of 0.5 you will be getting the maximum response, which means if the period of vibration of the structure is, let us say, 1 second, and if the rectangular pulse lasts for half a second, the full response, which will be twice the static response, that will be obtained. Similarly, we have got the halfway sine curve, which is having a maximum response ratio of about 1.7 or 1.65, and we have the triangular pulse going from maximum to 0 in the end, giving rise to a maximum response of about 1.6 or 1.65. So we say that this is the way the response can be represented for dynamic forces over here. There is another type of variation also indicated, that we have got over here the duration of the force versus the period of vibration on x-axis and the dynamic load factor. So for a rectangular pulse, if the duration is for a very small time, let us say, which is very small compared to natural period of vibration, structure doesn't get enough time to develop the full potential of the force, because by the time it tries to respond, the force is no longer there, so it develops very small amount of response. But if the force lasts for almost 0.4 to 0.5 of the period of vibration, then we say that the full response, which is 2 times the static response, is obtained. Similarly, for this triangular pulse, eventually the response meets the rectangular pulse, because if this time gets longer and longer, then it is more or less tending to be closer to rectangle, and so on and so on. So that is as far as the rectangular and triangular pulse is concerned. If you consider a pulse like this, so the force goes from 0 to maximum and then maximum to 0 again. And if we see on x-axis the time duration Td upon the period of vibration, and on y-axis we consider dynamic load factor maximum, which means the ratio of the maximum dynamic response to the response of the same force applied statically. So we see that the maximum ratio that we get over here is about 1.5. So for a triangular pulse, if the pulse remains for Td upon T equal to say about 1, then we say that almost maximum response is obtained. But if Td upon T exceeds 2 or 3 or 4, then we see that the response is not dynamic, because the structure is subjected to load which are varying very gradually and then drops down. So we say that there the dynamic nature is now more and more diminished. The result of that is we get dynamic load factor which is almost 1 when the ratio is 4, and so on. So that is as far as the effect of duration of the force which is a pulse type force. Now we consider single degree of freedom system subjected to ground motion. So far we were considering either the free vibration or the force vibration of the single degree of freedom system. Now we consider force vibration of a different category, that is developed due to the ground motion. So we represent the ground motion as x double dot g and the acceleration which varies with time, x as the displacement of the mass which varies with time. So we say that we have got the inertia force as mass multiplied by the relative acceleration x and the acceleration of the ground taken together, giving rise to total acceleration, while k into x is the spring force or the force in the columns due to the relative displacement x. So we consider terms on one side, that is the system generated forces. The acceleration x double dot is the relative acceleration, k into x is the relative, that x is the relative deflection, and m into x double dot g is the ground acceleration due to earthquake and so on, which is represented in terms of some reference value of ground acceleration into variation with reference to time. The solution of this equation is obtained using Duhamel's integral x equal to m into x double dot g0 upon m omega multiplied by r. So we now say that this is the way we get the solution of the problem where ground motion is to be considered for a single mass system. If we have got several masses and like a multi-story building, at each floor we have got a mass, and if I want to write down equation of motion for that, then we say that for each mass I will have to write down one equation because it has got separate displacement, separate accelerations and so on. So I will have several masses, several displacements, several accelerations and several springs. So with all that, now I consider this as a matrix equation. So I have got a mass matrix which represents all the masses in the system. X double dot g is the acceleration matrix for the masses, k the stiffness matrix for the structure, x the displacement vector for different degrees of freedom. We have got m the masses to be considered in the structure, also a mass matrix, and x double dot g of course is the ground acceleration. Usually when we have got such a large set of equations, then one way of splitting the equation is to use the model analysis concept, which we will not discuss in detail, only indicating that if the structure has got 100 degrees of freedom, then there are 100 independent modes which we can consider for the structure, and for that structure any arbitrary deflection that the structure otherwise undergoes or experiences can be split into modal deflection and their addition. So if I have got some displacements of the structure during vibration, y into phi, then we say that that deflection is split into y1 into phi1, which is y1 is some weightage given to first mode shape, which is phi1, y2 is weightage given to second mode into the second mode shape, and so on and so on. Same thing applies to acceleration vector. So any general acceleration can be considered to be made up of acceleration corresponding to first mode, corresponding to second mode, corresponding to third mode, and so on and so forth. So we now say that our entire concept is to split the overall response in terms of modal response and then consider its addition to that and so on. So we now consider the same equations with this split up of displacements and accelerations and pre-multiply them by the mode shape for nth mode. So phi n transpose, this is the split up of the modal acceleration, this is the split up of displacements, and on the left hand side I am multiplying by same phi n transpose m into x double dot g. Using orthogonality conditions and so on, we will be able to reduce the equation to one single term phi n transpose m into y double dot n multiplied by phi n, which is also the modal vector. Accordingly, we now get in this case phi n transpose m phi n as m equivalent, that is m equivalent. This is the m equivalent of that mass, that is phi n transpose m into phi n. Y double dot n is considered as a separate term. So I have got these three terms combined into this equivalent mass, these three terms giving rise to equivalent stiffness, and these terms on the right hand side phi n transpose m into x double dot g retained as they are phi n transpose mass, and x double dot g is taken as the reference value of acceleration into the time variation of the ground acceleration. So we now consider for this the equivalent mass M equivalent as phi n transpose M phi n, equivalent stiffness as phi n transpose K, and on the right hand side phi n transpose M, as that is for summation of all the masses for that particular mode, and so on. Now we consider the response of the structure which we have defined earlier, that the total response in dynamic state consists of the static response multiplied by dynamic load factor. So I have in this particular equation the static response to be considered by considering the force upon the stiffness over here. So now I say that I have got in this particular case the static response given by the force on the right hand side, and in the denominator I have got the stiffness. Actually the stiffness would involve K into the terms, but we have seen earlier that K upon M is omega square. So if I want K, then I can take it as M omega square, and that is what is taken over here, that M into omega square replaces K, and we have what is phi square as it is. So we now say that the dynamic response for that mode consists of the static response multiplied by the dynamic load factor that we have to consider for that dynamic nature of the force. If I want to consider, now this was for a mode, if I want to consider displacement of a specific point, then I will have to take the mode shape for that. So I am taking the earlier expression multiplied by mode shape factor for, say, for first floor or second floor, whatever it is. So accordingly I multiplied by this phi rn and get the displacement at rth mass point in nth mode of vibration. If I want to get from displacement the acceleration, because the system is vibrating, then we say that for simple harmonic motion the acceleration is omega square into x. In reality here the structure is not vibrating at a specific frequency, but if I am considering analysis in first mode, I will say that okay, though structure is not vibrating in first mode, I will still multiply it by frequency of the first mode and call that quantity as the pseudo acceleration of first mode. So at rth mass point the pseudo acceleration for nth mode is given by, so I will be considering the displacement multiplied by the frequency square, that is omega square. So we now say that we have got the acceleration or the pseudo acceleration at any mass point in any mode of vibration. If I consider that, then we say that as far as our analysis is concerned, we have got the pseudo acceleration. If I want to get from pseudo acceleration the pseudo force, then I will multiply that pseudo acceleration by the mass in that point, because mass into acceleration is the inertia force. So I have got the mass at rth point multiplied by pseudo acceleration, which is obtained from the earlier analysis of the displacements, multiplying it by frequency square. So we now say that the value of pseudo inertia force can be worked out. So this pseudo inertia force can be applied on the structure and the response of the structure can be determined. So we now say that if I want to determine the response of the structure, then what I need to consider over here, that these are all the fixed terms. There is this ground acceleration which I will have to consider depending upon the ground motion that I am considering, and the dynamic load factor, which of course I will have to determine depending upon the displacement time diagram that is supplied to me for the earthquake. So all of that is going to give me finally a dynamic magnification. Now the magnification in case of seismic analysis will depend upon the probabilistic concept as to if in that area where we are having the structure, whether many earthquakes have occurred. So our country is divided into different zones and some zone factors are indicated. Whether it is resting on a firm strata or very loose strata, because that will then accordingly generate different kind of local motion. So I will have to consider what type of soil strata is there. Further, for a given structure, I will have to consider the importance of the structure as to how much safety margin I will have to consider, what will be the effect of collapse of the structure, whether it will lead into large loss of life and so on. All those factors will go into determining the importance factor. And we have got the response reduction factor, because severe earthquake is one situation which may come in the lifetime of the structure. I don't want to design my structure to remain elastic under severe earthquake. So what I will do is I will take the severeness of the earthquake, use a reduction factor R, and say that my structure would remain elastic for that much fraction of the ground motion. So if severe earthquake is there, I will say that okay, let my structure get somewhat damaged, but if I reduce my ground motion by a factor R, then for that reduced ground motion, my structure must remain elastic. So I am using this response reduction factor, which is a concept given in the code itself. So we have to now consider all these factors to finally get the response of the structure over here. Now to determine the dynamic magnification factor, so what I will have to do is I will have to carry out the detailed dynamic analysis or the time history analysis, which will be too complex. So every time I may not be able to do it, or every time it may be tedious for anybody to do it. So there has to be some other method, and that other method is a response spectrum method, which we will see in detail subsequently. So we will consider a very simple example where time history analysis in modal space is considered, which means, say we have got a structure which is a 5-story building. So there are masses at these 5 locations. Each of the story has got some stiffness. Okay, so I have got this mass matrix, I have got this stiffness matrix. Okay, using that, now I will consider the free vibration analysis and determine its frequencies of vibrations and mode shape. So I have determined, for example, for first mode, its mode shape and its frequencies are indicated omega 1, omega 2, and so on. We have got the second mode, we have got the third mode, we have got the fourth mode, and so on. So all those 5 mode shapes are now shown graphically over here. Their values are tabulated over here. So we have got the mode shapes, the free vibration characteristics, and the associated frequencies. Having considered free vibration analysis, for carrying out seismic analysis, we require ground motion. So this ground motion is now considered, which is the north-south component of the El Centro earthquake, which has occurred in 1940 in California, USA. For this ground motion, for this structure, for every mode, the time history analysis is carried out and the results are indicated in this particular graph. So I have got first mode with its period of vibration. So for that particular mode, if I consider this as the input ground motion, then during the entire duration the response is obtained, and that response is shown over here in terms of, on y-axis you have got the displacement, and it is in real time that the basic variation is indicated. So we have in this graph time variation of the displacements. In this second graph that we have got, it is the pseudo acceleration, which means this displacement is getting multiplied by a frequency square of first mode, and that response is now shown over here. So we have got the displacement versus time diagram as a response of the structure, multi-degree of freedom system, but first mode response, second mode response, third mode, and so on. Over here, first mode acceleration, second mode acceleration, and so on and so forth are also considered. So we have got the displacement and pseudo acceleration variations for the ground motion. Then we have got 2 more additional responses. One is the base shear, because Once we have got the acceleration, we get the forces, mass multiplied by acceleration. Those forces we add from top to bottom, that will give us the base shear over here. And at this point, now we will say that we are considering the base shear and the fifth story shear for first mode, second mode, third mode, and so on and so on. So story shear is also considered and the base shear is also considered. So we say that for all those five modes, we are getting this variation due to the earthquake ground motion of the El Centro that we are considering over here. So in this case, we have considered El Centro ground motion and obtained the response versus time diagram, while roof displacement and overturning moment, again same variation is considered, and that displacement, now we see modal response is indicated in this case as first mode response, second, third, fourth, fifth, and this is now the total response that we are considering here, the maximum response. And over here the overturning moment is also considered, because we have the lateral loads applied at each floor, that lateral load into its distance from, or its height from the ground, so that is going to give rise to each mode the uh, overturning moment. The entire overturning moment is thereby considered. So we now say that the modal response is now considered. Now, having considered modal response, then we say that our objective will be to get the total response. So we have got the total response as addition of all those modal responses, and we will be getting the total response. So we now see that we will have to consider the time history analysis for each mode for that ground motion, and then the responses are together. So that is a very time consuming process. To circumvent this difficulty, mathematical difficulty, a response spectrum is now considered. Response spectrum analysis is introduced. Now each time we see that the response history analysis is very difficult. So each designer is not expected to carry out this time history analysis, which only researchers or the academicians can do. Then we will have to further indicate as to for which ground motion we will have to consider it, and highly sophisticated computations will have to be performed. To circumvent that, the response spectrum concept is introduced, which means if we have got to do the seismic analysis, though in response history analysis we get the entire time variation of a specific quantity, say maybe displacement or overturning moment and so on. But we are, as an engineer, not interested in the entire variation. We are interested in knowing only the maximum. But one value is required. It might generate thousands of values, but I don't want that. I want the maximum, because my structure has to withstand maximum of that response. So if someone takes this task and carries out time history analysis for any ground motion, once he spends a lot of time, someone or a team of we can say academicians or engineers, they come together and spend a lot of time in getting response to a specific ground motion for a structure with one specific period of vibration, with another period of vibration, and so on. Likewise, if several periods of vibrations are taken for that single degree of freedom system, and if a table is given or a simple graph is produced, that what is the variation of maximum response for different periods of vibration. Now this variation is represented or is named as response spectrum. It is the representation, if you see the definition, of maximum response of a spectrum of idealized single degree of freedom system of different natural periods, but having the same damping under the action of the same earthquake ground motion at the basis. The response referred to here can be maximum absolute acceleration, maximum relative velocity, or maximum relative displacement. So if that graph is available, then we say that our task would be very simple. Those graphs are fortunately made available by several researchers by course of practice. So I have got one such graph as a response spectrum curve in ACI. On x-axis, I have got natural period of vibration. On y-axis, if you see, it is the pseudo velocity. This curve is actually the response spectrum, and I have got this inclined line giving me the displacement variation, and a line perpendicular to that is the pseudo acceleration. So I have got the displacement, maximum displacement to be obtained, pseudo acceleration from here, and pseudo velocity from this. So if I have got a structure with some specific period of vibration, I will take it up to the curve. From this point, now we will see over here on this side I have got I have got the displacement, so I will know so much is the displacement. If I project it on this axis, I will be getting pseudo acceleration, and if I project it on this axis, I will be getting the velocity, pseudo velocity. So this response spectrum is able to give me for a given period of vibration the maximum displacement, the maximum pseudo acceleration, or the maximum pseudo velocity. The IS code also gives similar curve. So on x-axis we have got natural period of vibration, on y-axis we have got SA by G, which is the acceleration of the structure normalized to G, SA by G, in that particular equation where we require that value of G. And with this curve, if I know for a given structure its period of vibration, then we say that I don't have to go to the response history analysis, because someone has already spent a lot of time on that. He has given me this beautiful graph which gives me for a given period of vibration the value of SA by G, which I can use to calculate pseudo inertia force, pseudo bending moment, or pseudo overturning moment, and so on. Another curve is also given by the IS code, which is the response spectrum for equivalent static method. The earlier one was for the response spectrum method. So depending upon the method that you are considering, you can use that specific curve and then determine the maximum response of the given structure. Now we have the same system which we have considered earlier, 5-story frame with equal masses and equal stiffnesses at each floor. I have got a mass matrix, I have got the stiffness matrix, for which now I have already got the free vibration characteristics. Having got free vibration characteristics, now we have got those equations which give rise to finally the calculations for maximum displacement, maximum pseudo acceleration, or the pseudo velocity, and finally the pseudo inertia force, and so on and so forth. So we need only this, we can say the dynamic load factor from the response spectrum. So we take those response spectrum values, and for each mode we work out what are the responses. So we now say that peak model responses are obtained. So for first mode, second mode, third mode, and so on, I work out what is the displacements at mass point 5, what is the bending moment that is at the base, what is the shear force at the base. This is the shear force at the base, and this is the shear force at the topmost point or the fifth floor. So we add up all, we consider all these peak model responses and then determine what is the total response. Now this variation is indicated graphically over here. So we have got, in this particular case, if you have a look at that, here we have got the overturning moment at the base, we have got the displacement, maximum displacement at different floor level, and we have got the shear force at each of the floor level. So likewise for first mode, second mode, third mode, fourth mode, and fifth mode, all the responses are worked out. Those responses are the story shear, the displacement, the base shear, and the overturning moment over here. So for each mode we have got all these responses, and these responses are later on to be added to get the total response. So now we say that we have got over here the model response. Now I want to add all these model values to finally get the resultant response. So there are various schemes of additions. One is the absolute sum irrespective of their sign, whether it is plus or minus. You add them all assuming that they are all positive. Okay, now that is the kind of base shear that you will be getting. The shear at fifth floor level you will be getting, the overturning moment you are going to get, and the displacement at the topmost floor. If I use SRSS method, which is the square root of sum of squares, which is extensively used, very popular method, that is going to give me this base shear and so on. If I use the CQC, that is complete quadratic combination, which takes into account the time lag between the different modes and so on. So if all of that is taken into consideration, then this is another method of variation which gives total response which is slightly different than SRSS. And the response history analysis, which is the true result, then we say that that is what we have obtained using the response spectrum. But then we see that the response spectrum gives me, for example, the top maximum displacement of 6.8. SRSS gives me 6.8, here it is 6.847. So there is a difference in second and third digit and so on. So we see that these methods of additions are quite reliable and they are extensively followed. So this response spectrum makes life quite easy. You need only the frequencies of vibrations and the periods of vibration of the structure. Once the free vibration analysis is done, then we say that this response spectrum makes our job very simple, because it directly gives us the relationship between the period of vibration and the value of SA by G. So once we are very sure about the free vibration characteristics, that is period of vibration, then we say that the response spectrum is used to determine the total response of the given structure. So we now say that we have come to the almost conclusion of the presentation, and we say that the response spectrum method, which is a very powerful method and very popular method, makes the life easy, and it is all based upon the rational method of the response history analysis itself. Only the thing is, everyone is not expected to do response history analysis, but you will only do the free vibration analysis and then use the efforts of the other people to finally determine the system.